Hello. In this video, we are going to derive the pi conjugated system for cyclobutadiene using the Correspondence Theorem Method, also known as the KIM method. Here we have a quick sketch of the positions of the 4 carbon atoms in cyclobutadiene, and we've arranged them in such a way that it maintains the D4H symmetry that we imagine for this molecule. The dots show the positions of the carbon atoms that possess the pz orbitals that are normal to the plane of the screen, the pz orbitals that will make the pi conjugated system. So notice with the coordinate system that left and right is the x-axis, up and down is the y-axis, and then either coming towards us or behind the screen is the z-axis. A key requirement of the KIM method is to assign coordinates to the orbitals in question, and the only requirement is that these coordinates be consistent with the point group symmetry of the molecule, and we're imagining it to be D4H in this case. One important quantity that we need for this derivation is this permutation representation, delta 4. And since it's a reducible representation, it can be reduced into a linear combination of irreducible representations. Now, this can be done quickly in the KIM method because we just look for those irreducible representations whose basis functions are non-zero. And we will see in the following tables how we did this computation. But to summarize it here, we see this delta 4 is A1G plus B1G plus EU. And we remind you what their basis functions are below. Here is a complete list of the irreducible representations for point group D4H, showing a number of their basis functions. These are derived from Dr. Kim's book. Many tables of character tables will include some of these. They don't necessarily have all of them, even though one can derive them without much difficulty if you need to. Here in Table 3, we evaluate the A1G basis function x squared plus y squared at the 4 symmetry equivalent points in cyclobutadiene. So long as even just one of these is non-zero, then we know that we have to include the A1G irreducible representation in the permutation representation delta 4. In Table 4, we evaluate the B1G basis function x squared minus y squared at those 4 symmetry equivalent points. We see that none of these are 0. So we can conclude that B1G is included in the reducible representation delta 4, our permutation representation. Finally, we evaluate the EU basis function. X, we can use either X or Y because we have a doubly degenerate representation there. And we see that there is at least one of these that evaluates to be non-zero. Therefore, we know that the EU doubly degenerate irreducible representation is included in delta 4. And with that, we know that we have all four of the degrees of freedom that are in that reducible representation. Recall that we figured out that delta 4 can be reduced to the linear combination A1G plus B1G plus EU. For our reducible representation for pi bonding in the molecule, we have to multiply that by the irreducible representation that has z as its basis function. We use the z basis function because we're interested in the pz orbitals. And then we can multiply A2U times delta 4 and see that equals A2U plus B2U plus EG. And in this particular slide, we show the important basis functions that we're using, and we're showing exactly how we did the multiplication. We multiply basis functions, and then we notice that the new product basis function corresponds to a particular irreducible representation. Now we're going to evaluate each of those irreducible representations for pi bonding by evaluating the value of the basis function at those four different symmetry equivalent points. So we know, and these are values that we get are going to be the coefficients for a linear combination of those particular pz orbitals that span a particular irreducible representation. So the first one we do is for A2U, and we notice that each evaluates to be 1. So we're going to have a linear combinations where all the coefficients are equal to 1. Next, we do the same for the B2U basis function, quantity x squared minus y squared times z at the four different points. And we see that we get either a +1 or a -1 as the value of the basis, and that is going to be the value of the coefficient for that particular orbital, whether P1, the coefficient is going to be 1. For the P2 orbital, the coefficient is going to be -1, and so on. Next, we have the doubly degenerate EG representation, which has two different basis functions. And so first, we'll just use the first basis function, which is xz. And when we do that, we notice that we get values of 1, 0, or -1. So those are going to be the appropriate coefficients for each of the orbitals. Here we evaluate the second of the basis functions in EG, the YZ basis function. And now we see that we have coefficients 0, 1, 0, or -1. Note that we had to evaluate both basis functions within the doubly degenerate representation because we're trying to now work out what the pi bonding is. When we're just trying to figure out whether it was included in another representation, we only needed to evaluate one of the basis functions. Because if one worked, the other one would. If one didn't work, the other one wouldn't work either. So now using those evaluated basis functions as the coefficients, we see that for the A2U representation, we have P1 plus P2 plus P3 plus P4. For B2U, we have P1 minus P2 plus P3 minus P4. For the doubly degenerate EG representation, the first partner is P2 minus P4, and the second one is P1 minus P3. Note that we were able to derive each of the two representation orbitals separately. We didn't have to go from one to the next. Here we now draw what these orbitals look like, and we put them in order of energy. Our general rule is that the greater the number of nodes, the higher the kinetic energy, so therefore the higher total energy. For the A2U, there's no node, so it's the lowest in energy. The EG doubly degenerate representations each have one node. Note that the nodes are shown by a green line here. And then the highest energy pi orbital that we have is B2U symmetry, and we notice that it has two nodes. Since there are four PZ orbitals involved, we have four pi electrons, so long as we have a neutral system. And if we put them into the energy levels in order, we get 2 into the A2U non-degenerate state, and then we have 2 electrons that we put in one of the 2 EG orbitals. This assignment of electrons is problematic because we know by the Jahn-Teller theorem that if we have unequal occupancy of degenerate orbitals, the molecule will undergo a distortion so as to remove the degeneracy. So what would happen here, if this was really what's going on, the doubly occupied orbital that we showed to the left would go down in energy, and the one on the right-hand side would go up in energy. We would lift the degeneracy by distorting the molecule from a square shape to some kind of a rectangular or diamond type shape. From the theorem, we don't know exactly what the shape's going to look like after it distorts, but we do know that it is going to distort. Therefore, because of this Jahn-Teller distortion, we know that cyclobutadiene cannot exist as a D4H molecule, at least as long as it is a singlet. And in fact, cyclobutadiene by itself does not exist. However, if we were to, and also notice that when we had those 4 electrons, we had an anti-aromatic system, even at that. However, if we take the dianion of cyclobutadiene, now we have equal occupancy of the degenerate orbitals, so we're not going to have that Jahn-Teller distortion. And we have the magic 4n plus 2 Huckel number, since we have 6 pi electrons, that render this system aromatic. So it's going to be even more stable than it would be otherwise. I thank you very much for your kind attention. Stay healthy, stay safe, try to learn the Kim method, and as always, have a good one.